I like to start my days in the water. When I'm swimming, I'm often thinking about water quality, for obvious reasons, and efficiency. Efficiency is critical in swimming because it allows you to get further with less effort. And efficiency is important in our agriculture. When I think about efficiency in agriculture, I often think about the nitrogen footprint of our systems. The footprint's quite large in vegetable production systems in California. And I think we need to work to try to reduce the size of that footprint so that we can minimize the impact of our production systems on the environment. This is a study that was done that looked at the nitrogen footprint using this virtual nitrogen factor metric for different crops. And you can see for vegetables, it's several times what it is for other crops. I believe that a one-size approach to addressing water quality protection is not likely to work well across broad regions of California because of the different types of cropping systems. We need to make sure that the approach that's used fits well with the nitrogen footprint of the crop and the cropping system in that region. This is another study where they looked at the nitrogen footprint of organic versus conventional crops, and they didn't find much difference, although perhaps with vegetables, the footprint could be a little larger for organic vegetables than for conventional ones. Now, it's important for us to ask, why do vegetables have such a large nitrogen footprint? I think this graph can help us to understand that. This is a figure that was in a publication by Tim Harsh from several years ago up at UC Davis. And what this shows is the typical pattern of nitrate concentrations in the top foot of soil over the annual cropping cycle for coastal vegetable production. And you can see that we start off the season relatively low. And with our first spring vegetable, we add fertilizers, perhaps before planting and then a little bit later in the season. That helps to increase it, as well as microbial activity in the soil as the soil warms up more. And at the end of the season, for that first crop, we turn a lot of nitrogen-rich crop residues back into the soil. That helps to increase the nitrate levels again. And then we would add more fertilizers pre-plant as well as side dressing in our summer planting. And then again at the end of the summer crop, we turn our nitrogen-rich residues back into the soil. And we're left at the end of the season with a pretty high amount of nitrate, which increases and then peaks. And you'll notice then it really drops quite quickly. And the reason for this drop in the November to January period is basically because there's when we get a lot of rainfall. And the rainfall essentially washes the nitrogen out of the topsoil, and this is where we get problems with leaching into our aquifer. The reason for this large amount of loss of nitrogen is because of the fact that most beds in the valley are left bare fallow over the winter, and this leads to a lot of leaching, but we can also have big problems with soil erosion and runoff. This is a figure, a satellite image from a paper I wrote several years ago that was looking at questioning whether we could grow vegetables sustainably without cover crops. It's a complicated question, but I don't think we can. What you'll notice here is that in the middle of January, the area surrounding the valley is green, but there's relatively little green in the valley, and that's because of the lack of cover cropping during this fallow period. So I think it's fair for us to refer to this challenge here as a wicked and leaky problem. When I say wicked, I don't mean evil. What I mean is that wicked problems, these are challenges that don't have easy solutions. Things like homelessness, healthcare, climate change, those are all wicked problems. So how do we address this wicked and leaky problem? Well, I like to think about sponges when I think of leaky problems, because sponges can really help. And non-legume winter cover crops can basically act like nitrogen sponges. They can suck up nitrogen, hold it temporarily, and prevent it from leaching into the groundwater. One of the first publications I read on this cover crops for clean water, this was back before I started my job here, and I was looking through the paper that publication recently, and I noticed that there was this paper from 1949 that talked about the benefits of cover cropping for reducing nitrogen losses. We've been doing research on cover crops for a long time, and I thought that's important just to point that out. Now I'm going to go through three papers, or three different studies, I should say, from the Central Coast region that have looked at nitrogen leaching reduction with cover crops. The first was by Louise Jackson, and Louise and her team found there was a 65 to 70% reduction in nitrate leaching from winter cover crops compared with a fallow during the winter. Then there was another study in 2014 that looked at leaching reduction by a winter rye cover crop in a wet year and a dry year. And the numbers they found in the 64 to 75% range are very similar to what Louise Jackson's study had found. And more recently, I've been working with two PhD students from Stanford, and what we found was that nitrate levels at the 2 to 3 foot depth were much lower where we had a winter cover crop, and were much higher where we had bare fallow. There's also a lot of data from meta-analyses throughout the world that show the benefits of cover cropping. All of these meta-analyses conclude that non-legume winter cover crops can reduce nitrate leaching. But cover crops and sponges have limits. And what I'd like to do is talk about the dynamics of nitrogen uptake and release, but also some of the limits of cover crops. And I'll do that with some data from my long-term study. And this is 8-year averages, and I'll show you several different figures. So this is for a cover crop that's planted in mid-October through November or so, and then it goes over through the winter period. And you'll notice that the biomass production increases quite linearly as the cover crop grows. Now, if we look at nitrogen uptake by the cover crop, you can see that it doesn't follow the same pattern as what occurred with shoot biomass. Most of the nitrogen uptake occurs quite early on in the season, and it may peak around January, but basically it peaks much earlier than biomass production does. Winter cover crops in this area typically can't take out more than about 100 to 150 pounds of nitrogen. And that's important because if we have a situation like this where there's, about 100 pounds or so of nitrogen that could leach in the top foot of soil, then a cover crop can really help. But if this amount over here is in far excess of that, then a cover crop's ability to reduce leaching is much more limited. Now, I also want to show you a little bit about the carbon to nitrogen ratio changes of a cover crop. So this shows that the changes in the ratio, C to N ratio, are relatively similar to what happened with our biomass as the cover crop grows and it becomes more lignified and tough. The C to N ratio increases. And what we're really trying to do, if we want to make sure that the nitrogen isn't released too quickly from the cover crop when it's terminated, is we want to reach a C to N ratio of 20 to 1 or more. And that will ensure that when that cover crop is terminated and mixed back into the soil, the release of nitrogen through decomposition will not be too quick. And that's why even though the cover crop takes up the nitrogen temporarily, we can be quite confident that the risk of leaching for a C to N material of 20 or more is very low. And that's why that number was integrated into the nitrogen scavenging credit for winter cover crops here. I think it's fair to say that when Ag Order 4.0 passed and cover crop nitrogen scavenging credits were included, there was a lot of celebration because farmers now had a real big incentive to grow cover crops. But then not too long after, the Ag Order was remanded. And so here we are again, trying to basically encourage cover cropping to be able to get credits again. And my hope is that that will happen. Let me tell you a little bit about what the cover crop nitrogen scavenging credits did when they were in place here for the brief time before they were remanded. Well, those credits increased cover crop adoption and interest by growers. And that inspired novel cover crop research at the USDA where I work, as well as from collaborators with Stanford, UC Davis, and several of the other UCs, as well as the resource conservation districts and sustainable conservation. And all of that helped us to improve cover crop management and reduce the risks of cover cropping, which then fed back into increasing cover crop adoption and interest by growers. And ultimately, this really helped to improve water quality protection here. So how do we get to the root of this wicked and leaky problem? Well, the answer is in the question. It has to do with the word root. We need to put roots and shoots of non-legume winter cover crops back in these systems so that they can help to address this difficult period of the year when leaching is very likely to happen. So my hope is that quite soon there will be a return of the cover crop nitrogen scavenging credits. This would be great because it will add momentum back into cover crop adoption here, and that ultimately is going to lead to water quality protection for this region of California and hopefully other regions as well. Thanks for giving me the opportunity to share my ideas with you. Take care.